Hi, welcome to the ComSci 137 lecture. Sunny here. For this module, we will be discussing about the Internet. As we have discussed before, an Internet, the lowercase I, is two or more networks that can communicate with each other. The most notable Internet is called the Internet, the uppercase I. It is composed of thousands of interconnected networks. The figure shows the Internet as several backbones, provider networks, and customer networks. The top level, the backbones are large networks owned by some communication companies. The backbone networks are connected through some complex switching systems called peering points. At the second level, there are smaller networks called the provider networks. They use the services of a backbone for a fee. The provider networks are connected to the backbone and sometimes to other provider networks. The customer networks are networks at the edge of the Internet that actually use the services provided by the Internet. They pay fees to provider networks for receiving services. Backbones and provider networks are also called Internet Service Providers or ISPs. The backbones are often referred to as an international ISP, while the provider networks are often referred as a national or regional ISP. The Internet today is an internetwork that allows any user to become part of it. To access the Internet, you can use the telephone networks via the dial-up service or the DSL service. You can also use the cable networks. Today, it is prevalent to use the wireless networks. Large companies can directly connect to the Internet. This can be done if the organization or the corporation leases a high-speed one from a carrier provider. In the mid-1960s, mainframe computers in research organizations were standalone devices. They are also very big. Computers from different manufacturers were unable to communicate with one another. The Advanced Research Project Agency, or ARPA, was interested in finding a way to connect computers to reduce costs and eliminate duplication of efforts. In 1967, at an ACM meeting, ARPA presented the ARPANET. It is a small network of computers which use the interface message processor. By 1969, the ARPANET is a reality. UCLA, UCSB, Stanford Research Institute, and the University of Utah connected via software called the Network Control Protocol. In 1972, Vint Cerf and Bob Kahn, both of whom were part of the core ARPANET group, collaborated on what they call the Interneting Project. They wanted to link dissimilar networks so that a host on one network could communicate with a host on another. Cerf and Kahn's landmark 1973 paper outlined the protocols to achieve end-to-end delivery of data. This was a new version of NCP. This paper on Transmission Control Protocol or TCP included concepts such as encapsulation, the datagram, and the functions of a gateway. In October 1977, an internet consisting of three different networks, ARPANET, packet radio, and packet satellite, was successfully demonstrated. Communication between networks was now possible. Shortly thereafter, authorities made the decision to split TCP into two protocols, Transmission Control Protocol or TCP and Internet Protocol or IP. IP would handle datagram routing, while TCP would be responsible for higher level functions such as segmentation, assembly, and error detection. The new combination became known as TCP/IP. In 1981, the Computer Science Network was created for those ineligible to join ARPANET. In 1983, ARPANET was split into two networks, the Military Network or MILNET and ARPANET for the non-military use. In 1986, NSF sponsored the National Science Foundation Network, a backbone that connected 5 supercomputer centers located throughout the US. It officially replaced the ARPANET in 1990. In 1991, IBM, Merit, and Verizon formed Advanced Network and Services and built a new high-speed internet backbone called the Advanced Network Service Network. Today, we witness a rapid growth both in the infrastructure and the new applications. The Internet today is a set of peer networks that provide services to the whole world. What has made the Internet so popular is the invention of new applications, like the World Wide Web, multimedia, and peer-to-peer applications. Autonomous systems. Autonomous systems or AS are collections of routers whose prefixes and routing policies are under a common administrative control. Could be an ISP, a large company, a group of companies, or a university. It represents a connected group of one or more blocks of IP addresses called IP prefixes that have been assigned to that organization, and it provides a single routing policy to systems outside the AS. Sometimes you hear about peering and transit. In peering, two or more autonomous networks interconnect directly with each other to exchange traffic. They are usually free. In transit, one autonomous network agrees to carry traffic that flows between another autonomous network and all other networks. In peering, two ISPs only exchange the routes of their downstream customers, and neither can see the upstream routes of our peering connection. Because transit is a paid service, the provider will provide routes to the rest of the internet, including their downstream partners of our peers and upstream providers. Here's an example. There are 6 ISPs, but 2 of them are backbone providers, Provider C and Provider D. Here are their connections. Provider A and Provider B are peered, also Provider E and Provider F. However, if Provider A send a message to Provider F, he cannot go to Provider E. The route will be Provider A to Backbone C, Backbone D, to Provider F. Submarine cables were first laid in the 1950s, carrying telegraphic traffic, establishing the first instant links between continents. Subsequent generations carried telephone traffic, then data communications traffic. The left image shows a cross-section of a submarine cable. The right image shows how it actually looks like under the ocean. If you want to see the location of the submarine cables around the world, there's a good website to visit. It's www.submarinecablemap.com. Let's look around the website. Here, the lines that you see are the actual cable systems. Let's zoom in. Check what are the cable systems that connects the Philippines to the world. See one. Then click the line. Okay, this one is the EAC C2C. It was operational on December 2002. It is owned by Telstra. One of the landing points in the Philippines is in Batangas. Let's look again for another. This one. Okay, the Pacific Light Cable Network. It's owned by Facebook and Google. It's connected from Baler. Let's check another one. The Asia-America Gateway, commissioned in November 2009. Its length is 20,000 kilometers. The Philippine side is owned by PLDT and is connected in La Union. Let us continue. One of the cable systems connecting the Philippines to the world is the Asia-Pacific Cable Network 2 or APCN2. PLDT is one of its owner. Another is the Southeast Asia Japan Cable or SJC. Philippine side is owned by Globe. As we have seen earlier, the Asia-America Gateway, which PLDT is a part of. As you have seen, there are many different cable systems. But how do they connect? It's actually through Internet Exchange Points or IXP. They are physical locations to which internet infrastructure companies such as ISPs and content delivery networks connect with each other. I'll discuss about the importance of a local IXP. For example, I am a PLDT subscriber, and I'm going to send a message to someone using Globe. If there are no local IXP, the data will travel outside the Philippines somewhere where there is a common network with Globe before returning to the country. If there is a local IXP, my message will arrive faster since it will not leave the country. In the Philippines, we have a national research and education network, the PREGENET. We also have an IXP, the Philippine Open Internet Exchange. Both are being managed by the OST-ASTI. As you can recall, a protocol is a set of rules that govern data communications. What is communicated, how it is communicated, when it is communicated. The elements of a protocol are syntax, which is the structure and format of a data, semantics, which is the meaning of each section of bits, and timing, when the data should be sent and how fast they can be sent. Standards creates and maintains an open and competitive market for manufacturers. They guarantee national and international operability of data and telecommunications technology and processes. They can be by de facto or by fact, which have not been approved by an organized body but have been adopted as standards through widespread use. By de jure or by law, they have been legislated by an officially recognized body. Standards are primarily developed through standard creation committees, but they have a slow approval process. The next is forums, which speeds up acceptance and use of technology. People will comment and suggest on a proposed standard. Solutions are presented in standard bodies. The last one are the government regulatory agencies. Their aim is to protect public interest. An Internet standard is a thoroughly tested specification that is useful to and adhered to by those who work with the Internet. It is a formalized regulation that must be followed. An Internet draft is a working document with no official status and a 6-month lifetime. Upon recommendation from the Internet authorities, a draft may be published as a request for comment or RFC. Each RFC is edited, assigned a number, and made available to all interested parties. RFCs go through maturity levels and are categorized according to their requirement level. Steve Crocker invented the RFC. Here's an example. An RFC, during its lifetime, falls into one of 6 maturity levels. Proposed standard is a specification that is stable, well understood, and of sufficient interest to the Internet community. At this level, the specification is usually tested and implemented by several different groups. A proposed standard is elevated to draft standard status after at least 2 successful independent and interoperable implementations. A draft standard reaches Internet standard status after demonstrations of successful implementation. The historic RFCs are significant from a historical perspective. They either have been superseded by later specifications or have never passed the necessary maturity levels to become an Internet standard. An RFC classified as experimental describes work related to an experimental situation that does not affect the operation of the Internet. Such RFC should not be implemented in any functional Internet service. An RFC classified as informational contains general, historical, or tutorial information related to the Internet. It is usually written by someone in a non-Internet organization, such as a vendor. RFCs are classified into 5 requirement levels. Required, it must be implemented by all Internet systems to achieve minimum performance. Recommended, it's not required for minimum conformance, but it is recommended for its usefulness. Elective, it's not required and not recommended. However, a system can use it for its own benefit. Limited use, it should only be used in limited situations. They are mostly experimental RFCs. Not recommended, it's inappropriate for general use. Normally, they are historic. The Internet Society is an international non-profit organization formed in 1992 to provide support for the Internet standard process. The Internet Architecture Board is the technical advisor of ISO. It oversees the continuing development of the TCP/IP protocol suite. The Internet Engineering Task Force is a forum of working groups managed by the Internet Engineering Steering Group. They are responsible for identifying operational problems and proposing solutions to these problems. The Internet Research Task Force is a forum for working groups managed by the Internet Research Steering Group. They focus on long-term research topics. This is all for Module 2. Thank you.